This is part one of a two-part walkthrough Veterinary Epidemiology, built specifically for those of you sitting the ACVPM Epidemiology Specialty exam. Here's my promise for the next stretch. We're not going to memorize formulas as isolated strings of letters. We're going to understand why each one is built the way it is, because on exam day, the questions rarely say calculate PAF. They describe a herd, a study, and a decision, and you have to know which tool fits. Part 1 covers measures of disease frequency, association, attribution, study designs, confounding, and bias. Part 2 picks up diagnostic testing, likelihood ratios, and sampling. If you leave today able to reconstruct Levin's formula from scratch rather than recall it, you're in very good shape. Let's get started. Orient you to the roadmap so you know where exactly we're headed. We start with the 4 measures of disease frequency: prevalence, incidence risk, incidence rate, and odds. Everything downstream depends on getting those straight. Then the 2x2 table, which honestly is the single most valuable thing on this exam. Every association measure you'll be asked about falls out of those 4 cells. From there, we move into measures of association: risk ratio, odds ratio, rate ratio, and then attribution: attributable risk, population attributable risk, attributable fraction, and the population attributable fraction with Levin's full formula fully derived. We close part 1 with study designs, confounding, and bias. And just so you can plan your studying, part 2 handles diagnostic tests, likelihood ratios, true prevalence, sampling, herd sensitivity and specificity, and systems sensitivity. Let's get started with part 1. Pillars of disease frequency. Get these right, and much of the exam takes care of itself. Prevalence is existing cases over total population. It's a snapshot of burden. 2 things drive it: how fast new cases appear and how long they stick around. That second part trips people up. A disease with modest incidence but lifelong duration will show high prevalence. Incidence risk, sometimes called cumulative incidence, is new cases over the at-risk population at the start of the period. It's a probability, and it requires that everybody starts out disease-free. Incidence rate, or incidence density, uses animal time in the denominator. Units are cases per animal year. Reach for this whenever animals enter and leave the study at different times. And odds, P over 1 minus P. When P is small, odds and risk are nearly the same number, which is exactly why the odds ratio can stand in for the risk ratio in case control studies. The line to remember: prevalence is a snapshot, incidence is a movie. Bathtub is the mental model I want you to carry into the exam room. Prevalence is the water level in the tub. Incidence is the flow coming out of the tap. The level goes up if the tap runs faster. That's rising incidence. Or if the drain is slow, meaning animals stay sick longer. The level goes down when animals recover, die, or are culled. Notice that recovery and death both lower prevalence, even though one is good news and the other isn't. When the system is at a steady state and prevalence is low, prevalence is roughly incidence rate times mean duration. That relationship shows up in exam questions constantly. Chronic BVD persistent infection is the classic: high prevalence, moderate incidence, because duration is lifelong. Contrast that with Yonis, where a cohort study measures 3 new cases per 100 cow years. Practical takeaway: use incidence when you're asking about etiology or evaluating a vaccine or intervention. Use prevalence for burden estimation, surveillance, and resource planning. If you memorize one thing today, memorize this table. Rows are exposure, columns are disease. Cell A is exposed and diseased. Cell B is exposed and not diseased. Cell C is unexposed and diseased. Those are your background cases, the ones that would have happened anyway. Cell D is unexposed and healthy. Row totals: N1 is A plus B, all the exposed animals. N0 is C plus D, all the unexposed. Column totals give you disease positive and disease negative, and everything sums to N. From those four numbers, you get 6 measures immediately. Risk in the exposed is A over A plus B. Risk in the unexposed is C over C plus D. Odds in the exposed is A over B. Odds in the unexposed is C over D. Overall risk is A plus C over N, and exposure prevalence is A plus B over N. And the cross product rule: odds ratio equals AD over BC. The diagonals carry the entire exposure outcome relationship. Every measure we discuss for the rest of Part 1, RR, OR, AR, PAR, AF, PAF, flows straight out of these 4 cells. Ratios: 3 different jobs. The exam loves to test whether you can pick the right one. Risk ratio is risk in the exposed divided by risk in the unexposed. Risk ratio of 1 means no association. Risk ratio of 2 means exposed animals are twice as likely to develop disease. Risk ratio of 1/2 means the exposure is protective, a 50% risk reduction. Use it when you can actually calculate risk, which means cohort studies and randomized trials where you know the denominators. Odds ratio is the cross product, A times D over B times C. You use it when you cannot calculate absolute risk, like in case control studies where you selected cases and controls separately, so there is no true incidence denominator. Under the rare disease assumption, roughly 10% prevalence or less, the odds ratio approximates the risk ratio. Above that, it overestimates. Rate ratio compares incidence rates rather than proportions. Use it when follow-up time differs between groups. If Group A is followed 2 years and Group B 5 years, a simple risk comparison is unfair. The rate ratio fixes that because the denominator is animal time, not head count. So the decision rule: risk ratio when you can, rate ratio when follow-up varies, odds ratio when incidence simply cannot be determined. We shift from relative measures to absolute ones. This is where epidemiology starts answering the question a farmer or a policymaker actually cares about. How many cases? Attributable risk is risk in the exposed minus risk in the unexposed. It's the extra risk caused by the exposure, after you subtract the background risk that would have been there anyway. Units are cases per animal. Work the example on the slide. Exposed risk 25%, unexposed 10%, so attributable risk is 0.15. That's 15 extra cases per 100 exposed animals. Population attributable risk scales that to everybody. Population attributable risk is population risk minus unexposed risk, and conveniently it equals attributable risk times PE, the prevalence of exposure in the population. It answers, how many cases would disappear across the whole population if we eliminated this exposure? Note the relation. Population attributable risk is always less than or equal to attributable risk because not every animal in the population is exposed. And here's the public health punchline. A high exposure prevalence multiplied by even a modest attributable risk can produce a very large population attributable risk. Widespread exposures with unimpressive relative risks often deserve top priority. Attributable fraction moves us from absolute to proportional thinking, but still focused only on the exposed group. The definition: of the cases occurring in exposed animals, What proportion is actually due to the exposure rather than background risk? Let's derive it because the derivation is the memory aid. Start with attributable risk equals risk in exposed minus risk in unexposed. Substitute risk in exposed equals risk ratio times risk in unexposed. That gives attributable risk equals risk in the unexposed times the quantity risk ratio minus 1. Now divide attributable risk by risk in the exposed, which is risk ratio times risk in the unexposed. The risk unexposed terms cancel and you're left with risk ratio minus 1 over risk ratio. Sanity check the endpoints. Risk ratio equals 1 gives attributable fraction of 0, no effect. Risk ratio equals 2 gives 0.5, half the cases caused by the exposure. As risk ratio climbs toward infinity, attributable fraction approaches 1. Interpretation. Attributable fraction of 0.60 means 60% of cases in exposed animals would not have occurred without the exposure. The other 40% were going to happen regardless. Attributable fraction requires a risk ratio of at least 1. A negative attributable fraction is undefined. And keep the scope straight. Attributable fraction is the exposed group only. Population attributable fraction coming next is the whole population. Levin's formula. This is the one candidates most often memorize badly, so let's build it instead. Population attributable fraction is the proportion of all cases in the population that would be prevented if we eliminated the exposure entirely. Step 1. Population risk is a weighted average. PE times risk in the exposed plus 1 minus PE times risk in the unexposed. Step 2. Substitute risk in the exposed equals RR times risk in the unexposed. Factor out risk in the unexposed and you get risk unexposed times the quantity 1 plus PE times risk ratio minus 1. Step 3. Population attributable PAR is population risk minus unexposed risk, which simplifies beautifully to risk in the unexposed times PE times risk ratio minus 1. Step 4. Divide PAR by population risk. Risk in the unexposed cancels top and bottom, and you're left with Levin's formula. PE times risk ratio minus 1 over PE times risk ratio minus 1 plus 1. Let's use it. Risk ratio of 3, PE of 0.30. Numerator 0.3 times 2 equals 0.6. Denominator 0.6 plus 1 equals 1.6. 0.6 over 1, 0.6 is 0.375. So 37.5% of all cases in that population are preventable by removing the exposure. The key insight for exam scenarios. A common exposure with a modest risk ratio can outweigh a rare exposure with a dramatic risk ratio. Prevalence drives population impact. Put all 4 attribution measures side by side because exam questions live in the differences. Left column is the exposed group. Right column is the whole population. Top row is absolute measures. Bottom row is proportional. Attributable risk, absolute exposed group, risk in the exposed minus risk in unexposed, in cases per animal. Use it when you need the actual number of cases prevented in the exposed group. Population attributable risk, same units but scaled by exposure prevalence. AR times PE, always less than or equal to AR. Attributable fraction, proportional, exposed group RR minus 1 over RR. Use it when the question is about the strength of the causal role among those already exposed. Population attributable fraction, proportional, whole population. Levin's formula. This is your priority setting measure. What share of total disease burden does this exposure own? The clean mnemonic, AR and AF are exposed group focus. PAR and PAF are population focus. Absolute measures give you cases. Proportional measures give you fractions. You need both for a complete picture. Now to study designs arranged as a hierarchy of evidence. And remember, the design determines what you're allowed to measure. At the bottom, cross-sectional, exposure and outcome captured at the same moment. You get prevalence, prevalence ratio, prevalence odds ratio. You cannot establish temporality. So this is hypothesis generation and survey work. Next, case control. Start with the outcome, look backward at exposure. Odds ratio only. You cannot calculate risk. Very efficient for rare diseases, and control selection is the make or break challenge. Third, cohort. Follow exposure forward to the outcome. Now you get incidence rate, risk ratio, rate ratio, attributable risk. Temporality is established. This is the gold standard observational design. Fourth, the randomized controlled trial. The investigator assigns exposure, which eliminates confounding by design and gives you the highest internal validity. Measures include risk ratio, relative risk reduction, absolute risk reduction, and number needed to treat. At the top, systematic review and meta-analysis, but with a caveat. The quality of a meta-analysis is entirely hostage to the quality of the studies inside it. If you remember nothing else, randomized controlled trials eliminate confounding, cohort gives incidence and risk ratio, case control gives odds ratio only, cross-sectional gives prevalence only. Sectional studies in detail. Everything, exposure and outcome, collected at one point in time, no follow-up. What you can calculate: prevalence, prevalence ratio, and prevalence odds ratio. The prevalence ratio is the prevalence in the exposed over prevalence in the unexposed, interpreted just like a risk ratio where 1 means no association. Strengths are real. It's fast and cheap. One sweep of data collection. It's ideal for chronic or common conditions where burden is visible in a snapshot. It supports surveillance and resource allocation, and you can look at many exposures and outcomes at once. The weaknesses are what gets tested. First, temporality. You cannot tell whether exposure preceded disease, and temporality is the fundamental criterion for causation. Second, survivor bias. Only the animals still present are counted. Those that died or were culled are invisible. Third, Neyman bias, also called prevalence incidence bias. Acute cases that resolved before the survey never appear. On analysis, logistic regression gives you an odds ratio, appropriate when prevalence is at or below 10%. When prevalence exceeds 10%, prefer Poisson regression, which yields a prevalence ratio because the odds ratio will overstate the prevalence ratio. The question cross-sectional design can never answer: did the exposure come first, or did the disease change the exposure? Case control studies: efficient, widely used, and full of traps. The design: cases are animals with the outcome. Controls are animals without it, drawn from the same source population that produced the cases. Then you look backward at exposure. The key measure is the odds ratio, A times D over B times C. Strengths: outstanding for rare diseases because you find all the cases first rather than waiting for them. Fast and cheap compared to a cohort. You can examine multiple exposures at once. Great for early hypothesis testing. Interpretation depends on the rare disease assumption. When prevalence is under 10%, A is much smaller than B, and C is much smaller than D, so the odds ratio approximates the risk ratio. As prevalence climbs, the odds ratio overestimates the true risk ratio. Now the challenges. Control selection is the most critical. Controls must represent the source population. Hospital-based controls invite Bergson's bias when the reason for admission is itself linked to the exposure. Exposure measurement is retrospective, which opens the door to recall bias, since cases often remember or actively search for past exposures more than controls do. Mitigate by blinding interviewers to case status and favoring objective records over owner memory. On matching, match on confounders like age, sex, and breed to improve efficiency, but you must then analyze with conditional logistic regression. Standard logistic regression throws away the match structure, and beware, overmatching on anything sitting on the causal pathway, you'll erase the very effect you're studying. Bottom line, case control trades causal clarity for efficiency, and the odds ratio is the only measure you can calculate. Cohort studies come in two flavors, and knowing the difference is straightforward exam points. Perspective: enroll disease-free animals, classify them by exposure, then follow them forward and record new disease events as they occur. Retrospective or historical: the exposure and outcome have already happened, and you mine existing records, medical records, farm databases, looking back. Perspective strengths: temporality is unambiguous. Exposure definitely precedes the outcome. You measure incidence directly, so incidence rate, risk ratio, rate ratio, attributable risk, and PAR are all on the table. You can study multiple outcomes at once. It's the gold standard observational design for causation. The costs: expensive, slow, and you need a large sample for rare disease. Loss to follow-up is the major bias threat, so track your animals carefully. Retrospective strengths: fast and cheap, no waiting, and you can span long periods that have already elapsed. Critically, you can still calculate true incidence, which case control cannot. The weakness is that you're captive to whatever was recorded. Data quality and consistency are out of your control. Either way, the key advantage over case control is real incidence rates, which are far more informative than odds ratios, both for etiology and for explaining risk to a client. Randomized controlled trial, the gold standard for causation and the only design that handles unknown confounders. 5 components. First, randomization. Animals or herds are assigned by chance to treatment or control. This distributes both known and unknown confounders equally. No other design does this, and that's the defining advantage. Second, blinding, ideally double blind, though in veterinary trials we're often limited to single blind with the observer blinded. Blinding prevents observer bias in outcome assessment. Third, the intervention itself, treatment to one arm, placebo or standard of care to the other. Fourth, follow-up. Track outcomes in both groups for a specified period and document every loss to follow-up. Fifth, analysis. Intention to treat means you analyze every randomized animal in its assigned group regardless of compliance. It preserves the integrity of randomization and prevents overestimating the benefit. Per protocol analysis can be informative, but it can also reintroduce bias. Key outputs: risk ratio, relative risk reduction, which is 1 minus risk ratio, absolute risk reduction, which is the attributable risk, and number needed to treat, 1 over the ARR. One ethical point that shows up on exams: clinical equipoise. There must be genuine uncertainty about which arm is better before you enroll. Confounding, and I want to start with the distinction that matters the most. Confounding is not bias. It's a real structural phenomenon in the data. Three criteria, and a confounder must meet all three. One, it's associated with the exposure. Two, it independently predicts the outcome, even among unexposed animals. Three, it is not on the causal pathway. It sits outside the exposure to outcome arrow, not inside it. The classic veterinary example is herd size. A study finds vaccination is associated with lower disease, but large herds are more likely to vaccinate, and large herds also have more disease from stocking density. Herd size satisfies all three criteria. Confounding runs in both directions. Positive confounding inflates the apparent association and overstates risk. Negative confounding masks or dilutes a true effect and understates a benefit. How do you detect it? Compare crude versus adjusted estimates. On the slide, the crude risk ratio is 1.8 and the adjusted is 2.4. A difference greater than roughly 10 to 15% means confounding is present. The Mantel-Hansel approach. Stratify by levels of the confounder, calculate the risk ratio within each stratum, pool the strata as a weighted average, and if the pooled estimate differs from the crude estimate, confounding is confirmed. And here's the good news that separates confounding from bias. Because it's structural, you can control it analytically after data collection. Selection and information bias, you cannot. 6 methods to control confounding, and they split into 1 that prevents and 5 that correct. Randomization is the gold standard because it distributes known and unknown confounders alike. It's only available in experimental studies. Restriction, limit enrollment to a single level of the confounder. Dairy cows only removes breed confounding entirely. The trade-off is generalizability. Matching, pair each case with a control, sharing the confounder value. It improves efficiency, but you must analyze with matched methods. Conditional logistic regression. You cannot match and then ignore the match. Stratification. Analyze within each stratum and pool with Mantel-Hansel. Best for a small number of categorical confounders. And it's transparent. You can see the effect inside each stratum. Multivariable regression, adjust for many confounders at once using logistic, Poisson, or Cox models. Most flexible, handles continuous confounders, but respect the rule of thumb of at least 10 outcome events per variable in the model. Propensity scores, model the probability of exposure, then match or weight on that score to balance the groups. Useful when you have many confounders in observational data. It mimics the balance of an RCT. The sentence to carry out of here, randomization prevents confounding. Everything else controls it after the fact, and only for the confounders you actually measured. Bias, systematic error, and it comes in 2 families. Selection bias is about who gets into the study and who doesn't, in a way that relates to both exposure and outcome. Bergson's bias, cases and controls, both drawn from hospital populations, where admission itself is linked to exposure, creating a spurious association. Niemann or prevalence incidence bias. A cross-sectional study misses acute cases who died or recovered before the survey. Lost to follow-up bias. Animals are more likely to drop out if they're both exposed and doing badly. And the healthy worker effect. Exposed workers look healthier because the sick ones leave the exposed role, which underestimates risk. Information bias is about how accurately you measure exposure or outcome. Misclassification comes in 2 forms. Non-differential, which usually biases toward the null, and differential, which can push the estimate in either direction. Recall bias is differential by nature. Cases remember past exposures better than controls. Observer bias. Knowing exposure status colors how the observer records the outcome. The fixes differ, and this is the exam point. Information bias is preventable through blinding, objective measurements, standardized protocols, and validated instruments. Selection bias cannot be fixed in analysis. It must be prevented in the design. Once it's baked in, it's irrecoverable. Validity in two flavors, and the order matters. Internal validity asks, were the results correct for this study population? A study with perfect internal validity gives the true effect estimate, free of systematic error. It's threatened by exactly three things: selection bias, information bias, and confounding. External validity or generalizability asks, can I apply these results elsewhere? It's threatened by highly selected populations, unusual exposure levels, and atypical management. Findings from elite dairy herds may say nothing useful about subsistence farming. Note that you can have perfect internal validity and zero external validity. The reverse isn't useful. A study with poor internal validity tells you nothing, no matter how representative the population is. So the hierarchy is, first, is the effect real? Then, does it apply here? One more concept that lives next door: effect modification, also called interaction. That's when the association genuinely differs across levels of a third variable. Unlike confounding, this is a real biological phenomenon, not a distortion to be removed. If vaccine efficacy is higher in young animals than old, you report the results stratified by age. You never pool and hide the difference. The quote on the slide is worth memorizing. An unbiased answer to the wrong question is worthless. 10-step outbreak investigation framework. Expect to see this tested as a sequencing question. Step 1, prepare. Safety, team, permissions, supplies, PPE, diagnostic kits, notification of contacts. Step 2, establish that an outbreak actually exists. Compare observed cases against expected baseline for this, population, and time period. Step 3, verify the diagnosis. Clinical signs plus laboratory confirmation. Rule out lab error before you chase an artifact. Step 4, define a case using time, place, and animal criteria. Start broad and sensitive, then tighten as you learn more. Step 5, find cases. Active case finding and align listing with all the key variables. Step 6, describe and orient the data by time, place, and animal. Time is your epidemic curve. Place is your spot map. Animal is species, age, breed, production type. Step 7, develop hypotheses about source, vehicle, and route, and check biological plausibility. Step 8, evaluate analytically, attack rate analysis, or a cohort or case control study nested within the outbreak. Step 9, implement control. And note this, you act on the hypothesis before you have full proof. Time pressure demands it. Step 10, communicate. Written report, stakeholder notification, regulatory reporting. Grouping them, 1 through 5 is situational awareness, 6 through 8 is analysis, 9 and 10 are action and accountability. Control does not wait for the analysis to finish. Curves. The shape of the curve tells you the transmission story, and this is a very common exam figure. Point source, a narrow single peak. Every animal is exposed at the same moment, and the width of the curve is roughly 1 incubation period. Think of animals drinking from a contaminated trough at a single event. Continuous common source, a plateau, then a sharp drop. Cases keep appearing while the source stays contaminated, and they stop abruptly when you remove it. Think of an ongoing contaminated water supply. Intermittent common source, irregular spikes with quiet troughs between them. Each peak corresponds to a distinct exposure event, contaminated feed delivered in separate batches, propagating successive waves that get wider and larger, each generation about one incubation period apart, growing as more susceptibles are drawn in. Foot and mouth disease spreading herd to herd is the picture here. 3 practical uses. Estimate the incubation period by counting back from the onset to the probable exposure. Pay attention to outliers. Early cases are often index cases. Late stragglers suggest secondary transmission. And use the curve to judge your control measures. It should decline after an effective intervention. A rising tail means control has failed. P-values and confidence intervals. Precision of language matters enormously here because the exam will offer you a plausible sounding wrong definition. The p-value is the probability of observing a result at least this extreme if the null hypothesis were true. It is not the probability that the null is true, and it is not the probability that your finding is a fluke. The correct wording is on the slide. If there were truly no association, would see a result this extreme by chance only X% of the time. Treat P as continuous, not as a pass-fail gate. The 0.05 threshold is convention, not scientific law. What the p-value never tells you, effect size. A large study can make a trivial difference statistically significant, and clinical importance, which is a separate judgment entirely. And a single p under 0.05 is not proof of reproducibility. The confidence interval does more work. Formally, repeat the study 100 times, and the true value lies inside 95 of those intervals. It gives you significance and precision in one object. If the 95% confidence interval for a risk ratio excludes one, you're significant at alpha of 0.05. Width tells you precision. Wide interval, small sample, be cautious. Narrow interval, large sample, trust the estimate. The rule: always report the confidence interval alongside the p-value. The confidence interval tells you how big and how certain. The p-value alone tells you neither. Program evaluation, and the theme is that screening always looks better than it is. The goal of screening is to detect disease at a preclinical stage where intervention is more effective, before clinical signs appear. 3 biases confirm to flatter screening. Lead time bias. You detect the same disease earlier, so survival from diagnosis looks longer, but the endpoint is unchanged. The defense is to compare disease-specific mortality, not survival time from diagnosis. Length bias. Screening preferentially catches slow-growing, milder disease because aggressive, fast-moving cases surface clinically between screening rounds. The screened group looks healthier than it is. Overdiagnosis bias. You detect disease that would never have caused clinical signs in that animal's lifetime, leading to unnecessary treatment and cost. For program validity, the Wilson and Jungner criteria all have to be met. The disease is important, its natural history is understood, the test is valid and reliable, it's safe and acceptable, it's affordable, and follow-up and treatment facilities actually exist. On cost effectiveness, number needed to screen is 1 over the absolute risk reduction times 1 over coverage. Higher risk reduction and higher coverage give better value per animal screened. And remember, a one-time survey is not a screening program. Screening is an ongoing, repeated process. The key principle: all 3 biases push in the same direction, making screening look more beneficial than it is. Always evaluate mortality outcomes, not survival from detection. One-page formula sheet. If you photograph one slide from part 1, make it this one. Frequency, 1 through 4. Prevalence is cases over population. Incidence risk is new cases over the at-risk population at the start. Incidence rate is new cases over the sum of animal time. Odds is P over 1 minus P. Association, 5 through 7. Risk ratio is A over A plus B divided by C over C plus D. Odds ratio is A times D over B times C. Rate ratio is incidence rate in the exposed over incidence rate in the unexposed. Attribution, 8 through 11. Attributable risk is risk in the exposed minus risk in the unexposed. Population attributable risk is population risk minus the unexposed risk, which equals AR times PE. Attributable fraction is risk ratio minus 1 over risk ratio, equivalent AR over risk in the exposed. And the population attributable fraction is Levin's formula, PE times risk ratio minus 1 over PE times risk ratio minus 1 plus 1. 12 is your intervention measure. Number needed to treat, 1 over the absolute risk reduction. 3 organizing principles. Everything flows from the 2x2 table. AR and AF are exposed group focused. PAR and PAF are population focused. And the odds ratio only approximates the risk ratio when disease prevalence is under 10%. Close part 1 with the 8 things I want you most to carry into the exam. 1. Prevalence captures burden. Incidence captures causation. Know which question you're asking before you pick a measure. 2. The 2x2 table is the engine. Every association measure comes out of it. Memorize it cold. 3. The risk ratio is your preferred measure of association whenever you can calculate it. The odds ratio is the fallback for case control designs. 4. AR and PAR are absolute. They tell you actual cases preventable. AF and PAF are proportional, the fraction of disease attributable to the exposure. 5. Levin's formula isn't magic. It's derived. It falls out of writing population risk as a weighted average of exposed and unexposed risk. 6. Confounding is a real data phenomenon, not a study error, and it can be controlled analytically after data collection. 7. Selection bias cannot be fixed in analysis. It has to be prevented in design. No post hoc adjustment undoes it. 8. Statistical significance is not clinical importance. Always read effect size and precision together. In part 2, we pick up diagnostic testing, likelihood ratios, true prevalence, sampling, and herd and system sensitivity. Thanks everyone. Take a short break and I'll see you for part 2. If this helped, please like, subscribe, and share for more.